Okay, so let's see. Yes, okay, so this seems fine. This seems great. How can we possibly make this hard? Let me show you. Let me show you how we can make this confusing. So this is tricky because problems, so physics problems, typically give you polar coordinates. You know, the boat is moving along the 45 degrees north of west or whatever, and that's how you find out. Oh, God, I don't know why this isn't ringing. I don't understand. I'm sorry. Oh, Lord. Let's see. Okay, some of these we'll talk about later. Rest your hand for a minute. What are the symbols besides meters per second? Okay, we did that now. That's I hat and J hat, right? Yeah. Will problems on the practice test deal with angles in degrees or radians? Good question. We're going to start out in degrees. We may get to radians eventually. Okay. What are the curvy unit vector arrows are? Yeah. So, So those are the unit vectors. Well, yeah. That little hat. This thing is a little. It's a caret. It's an upside down V. That little thing on top. Okay. So problems give you polar, but to do the physics, you need Cartesian. And to do physics is sort of a loose freshman physics, what I mean, to do the kind of problems we're going to do, okay? So for example, what we're going to do is we're going to learn to go back and forth, okay? So say you're given a problem. So problems give you polar. So let's look at a problem where we're given polar. Let's say we have a vector that looks like this. Again, looks basically the same. We have a velocity vector like that. And we're told how long it is. So there's the magnitude, my little v with a bar around it, and we're told the angle, theta, right? So that's what you get in a problem. We want to convert to Cartesian. So what you do is draw yourself a Cartesian coordinate system right on top of it like that. There's x and there's y, right? And then you use SOHCAHTOA, right? So hopefully, did you all hear about SOHCAHTOA? How many have ever heard the word SOHCAHTOA? Yay. I don't know what story they tell you now. Probably not the one that I learned in the 80s. Unlikely. So its sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Right? It's just a way to remember all these little relationships. And that's true for a right triangle. Right? So what you do is you say, I know my two components look like this. There's the Vx I hat component. There's the Vy j hat component. And now we're going to move it over like that. There's the Vy component there. This is the Vx component here. So all I did was slide it over to make a right triangle. Right? So then I don't care which one to do, but let's do cosine first. Cosine theta is adjacent over hypotenuse. Adjacent is Vx. And now here's your first test of your ability to do mathematical numbers. Don't put V, put V in the bars. The magnitude of V. Get some practice writing the right thing. You don't want to put a vector in the denominator of a fraction and think it's going to make sense. Right? Cosine theta is a scalar. This is a scalar and this is a scalar. So a scalar divided by a scalar makes a scalar. The scalar divided by a vector, if you left those off, I don't know what that is. That's confusing. Okay? So write it correctly, and then you can easily solve for this component. Vx equals the magnitude of V times the cosine of theta. Right? And then you're familiar with sine of theta, V y over v. Sine is opposite over hypotenuse, so Vy equals the magnitude times the sine of theta. Right? So that's how we can get, so if you're given, polar coordinates, you have the angle and you have the magnitude. And this is how you take the angle and magnitude and you get the Cartesian coordinates from those two. Right? You've probably seen that in some trigonometry class or something like that. Right? So you say, oh, how could they make that hard? Oh, okay, well, let's see if we can make it hard. So you might be given a problem, and they might say, look, the velocity is this way. Right? And then what are you going to do? This is like, we're going to find out, who you really are here. You're going to say, well, let me draw a Cartesian coordinate system like this. Okay. He said to put it at the origin, and then what did he say? I don't know. Nobody's listening. Then you put an angle on there, and you can say, well, I guess I'll put the angle here. And you can. if you know what you're doing, right? So you say, okay, well, this was the magnitude of v. That's fine. Here, sorry, that's ugly, right? And you say, okay, I need the two components. Well, I need this component. That looks like the y component. And I need this component. And if you apply SOHCAHTOA, you'll get pretty close, right? So we say, well, sine is opposite over hypotenuse. So we say, oh, the Vx is the magnitude I was given times the sine of theta in this case. But that doesn't match the standard version, right? It doesn't match because you define angles from the x-axis, not from the y-axis. You can define it from the y-axis, but then you've got to use SOHCAHTOA to get your own formula here. Okay? And you also have to watch your negative signs if you make up your own theta version. Because is this positive or negative? Well, it's negative, right? If you plugged in the numbers, you might get, oh, it's 3 meters per second. And the way you're going to get it is you're going to go, oh, it's to the left. Right? 99% of us do our negative sign that way. I did a triangle. I know this side of the triangle is 3 meters per second. And I know it's to the left because it's pointing to the left. So I put a negative sign. That's okay. You can do it that way. That's how most people do it. Now, when you get into really complicated problems with like 20 angles, you might start to get messed up. But for most of what we're going to do in this class, you can just do that. But if you're a rule, how many rule followers do we have here? See, I'm not raising my hand. Okay, that's good. It's good to be a rule follower. If you're a rule follower, you say, well, this is what they gave me. I want to say this angle. I'm going to add 90 to it. And then you can go straight with these formulas that let you sleep better at night, right? So if this was 30 degrees, and the sine of 30 degrees is, I'm going to say a half. I forget which one it is. Say it's a half. You know it's negative half. If you say, oh, no, I'm going to do 120. I'm going to do 90 plus 30 is 120, and I'm going to follow this standard formula. You'll get negative a half. Right? So going the standard definition, in addition to getting the angle right, will also give you the negative sign. You won't have to put it in artificially. Okay? So just watch. Problems don't always give you the angle counterclockwise from here. They'll give you the angle other ways. Okay, let's see. And then, of course, the y component, you'd have to say, okay, well, I use SOHCAHTOA to get Vy, cosine theta, because y is adjacent over hypotenuse, and you'd have to use your knowledge to say that one's positive. I'll get some positive number here, and it's positive. That's how you'll know. All right. Let's see. Is Vx a vector component? Does that make it equal to the magnitude? Oh, my God, no. So let's do it again. Components are not the same as magnitude. So magnitude is the idea that applies in polar coordinates, and it is the length of the vector. It is literally, get a ruler out. How long is the vector? It can't be negative long. Does your ruler have a negative side on it? No. You can measure a displacement negative, but you're not going to measure a length with a ruler that's negative. So the magnitude is always positive. The component can be negative because it's just a scalar that describes an axis. Okay? So let's think about this for a second. If we wanted this vector to go the other way, let's describe this vector now. How would we describe this vector? It'd be like the same magnitude, but we'd add 180 degrees to the angle. Right, so if you want to make this negative, you change the angle, but this can't be negative. If you want to make this negative, and you want it to go the other way, you put a negative sign on the two components, because they can be negative. Okay, so there's a very big difference between those two things. And it's very easy to mix up. That's why I'm like making a big deal about it. It's very normal that you would mix that up. All right. So that is how to go. That's only one way, right? That's how you have polar and you need Cartesian. Then you do all the physics in Cartesian, and then the stupid problem. Yeah, go ahead. Yes. Yeah, you can do it any way you want. You can define theta from any way you want. If you do your own SOHCAHTOA, if you do your own SOHCAHTOA triangle, you can do anything you want and get the negative signs right. You could even say, this isn't 90 plus 30. This is negative 180 plus 60. And then use these formulas if you want. Right. Yeah. So yeah, you can do it any way you want. Just, you got to get the negatives right. So now we got to go the other way. So we do all that. We get it in Cartesian. We do the physics. We get the answer. And then the stupid problem says, give the answer in polar coordinates. Right. So now we got to go back. Right. So let's see. So the answer in polar coordinates. So this is the case where we have the vector answer now, right? And we know it's x component, and we know its y component like that. We know those two numbers, so we got to go the other way. We got to go the other way. All right. I meant to, let's here. Oh, sorry. Let's do it down here. Let's make it more exciting. There's Vx and there's Vy. Right? I did not make the symbol negative. Vy is a variable. It can be positive or negative. Okay, so I just wrote Vy down there. I didn't write it negative. Okay, so we have Vx and Vy. We want, what do we want? We want, damn it, we want those two things that were there. We want the magnitude and the angle. So the magnitude you get from the Pythagorean theorem, right? So this makes a triangle, Vx, Vy, right triangle. The square root of this squared plus this squared is that. So it's just the square root of Vx squared plus Vy squared. Like that. Is there any way you can get a negative number from this? Okay, well there is, but no, there's not. There's not. Okay, yeah. Y. These are components. Vx squared plus. Oh yeah. Oh my God. What? Yeah. This is Vx, and then I'm sliding over, and this is Vy. Thank you. There you go. Yeah. So it'll always come out positive, just because the magnitude always has to be positive. If you put two real numbers in there and you square them, they've got to be positive. You take the square root, it has to be positive, so it'll be positive. And then you get the angle, you go back to your SOHCAHTOA, the last part, right? Theta is the inverse tangent, and that freaks people out, but it's really not that bad, of the y component over the x component, right? So here's your right triangle, there's your angle. The tangent of that angle is opposite over adjacent, Vy over Vx. So we just take the inverse tangent and you get that, okay? And if you had numbers like this, if you plugged in a positive Vx and a negative Vy, you'd get a negative number, and the inverse tangent of that negative number would be a small negative angle, because we're following the mathematical convention here. It's be a small negative angle relative to the horizontal axis. But this formula also depends on how you set it up. You know, you could come over here and say, I have this Vx and Vy. What's the angle if I do the formula for this right triangle, and you do an inverse tangent, you'll get this angle. But if the book says, what's the angle relative to the horizontal, you got to add 90 to it. So you just got to, you can use SOHCAHTOA all you want, but just think carefully about what you're being asked sometimes. And there's nothing tricky like that on purpose, but that's just how it works out. Let's see. How can you use SOHCAHTOA for the larger angle if it's not right triangle? Then you flip it over and you do the right triangle the other way. Okay, so SOHCAHTOA is only for a simple right triangle. Right, so somebody's asking basically, here's a right triangle. What if the angle is here? I mean, I can't make a right triangle anymore. Well, now this is your right triangle. So you can always make a right triangle between a vector and two perpendicular axes. It's always possible. It just may not be where you want it to be. Mm-hmm.
So in the example that we just did, where did the I hat and J hat come in? Or are those not valid?
The example we just did, so here we go. Here, if I wanted to formally write this out, I would have said V is Vx I hat plus Vy j hat. I never actually said that, but that's how you write it out. When we use I hat and j hat or something, it's one of those, you just got to use it. When you use it, you'll get used to what it means. I'm going to try to explain, but until you use it, it's just, the hell's that, you know? How did you get the formula for answering in polar? These two, so this is the Pythagorean theorem for a right triangle, right? And this is the fact that tangent is opposite over adjacent for a right triangle. Those are just properties of right triangles. Took me straight to those. So we're not going to go refigure all that out. All right.